In this video, we're going to visualize one of the most fundamental and fascinating concepts in linear algebra, eigenvalues and eigenvectors. We'll use Mathematica to bring these abstract ideas to life. In general, when a matrix multiplies a vector, it usually changes both the direction and length of the vector. Consider this 2 by 2 matrix. When it multiplies the vector 1, 2, it transforms it into the vector 3, 2. Black color vector is the original vector, and red color is the vector transformed by the matrix. The vector is rotated and stretched when it multiplies. The vector -5, 1. It transforms it into the vector -4, -4.5. The vector is rotated and stretched when it multiplies the vector -2. It transforms it into the vector -3, -2.5. The vector is rotated and stretched. Now, observe this transformation. The black vector is transformed into the red vector by the same matrix. In this case, the direction stays exactly the same. There is no rotation, only stretching. Here's another example. This time the direction is reversed, but still lies along the same line. Again, no rotation. The transformed vector is shortened. These two special vectors, which retain their original direction after transformation, either in the same or opposite direction, are called eigenvectors of the matrix. The scalars by which they are stretched or compressed are called the eigenvalues.
So, we have the following definition. For a matrix A, a vector V, and a scalar lambda, if a dot V equals lambda times V, then V is called an eigenvector, and lambda is its corresponding eigenvalue. This relationship can be written, as shown here, where I is the identity matrix. Now, here's a key theorem. The characteristic equation of matrix A, used to find its eigen, is given by determinant of lambda times I minus A equals 0. Eigensystem is the function of Mathematica to find both eigenvalues and eigenvectors of a matrix. Let's walk step by step through the pedagogical derivation of the eigenvalues and eigenvectors of this matrix. A equals 1, 1, 1.5. We'll first compute the eigenvalues using the characteristic equation, and then derive the eigenvectors algebraically. We start by solving determinant of a minus lambda, I equals 0. Here, lambda is the eigenvalue, and I is the identity matrix. So we compute A minus lambda I equals 1 minus lambda 1, 1.5 minus lambda. Now take the determinant, 1 minus lambda times 0.5 minus lambda, minus 1. Multiply it out, as shown. Lambda squared minus 1.5, lambda minus 0.5.
That's our characteristic equation. Now, solve using the quadratic formula. So the two solutions are the eigenvalues, lambda 1 and lambda 2. These match the eigenvalues. Calculated in Mathematica, let's find the eigenvector V equals xy, corresponding to each eigenvalue. for lambda 1. Solve the equation. A minus lambda 1, I times V equals 0. This gives us this matrix. From the first row, y equals 0.78078 times x. That gives the first eigenvector, which in normalized form is same as given by Mathematica. Now for lambda 2, a minus lambda 2I gives this matrix. And therefore, we have equation of y in terms of x, so the normalized eigenvector matches the Mathematica output.